So we can think about a solution forming as being composed of three different steps. So the first step is taking the solute particles and pulling them apart from each other, right? Because they're attracted to each other, that's why they're stuck together as maybe a solid. So this is always going to be endothermic. You have to put energy into it because you have to overcome the intermolecular forces to pull those molecules apart. So this is the change in energy for the solute getting pulled apart. That's going to be a positive number. The next step we can envision is separating the solvent molecules to make room for the solute molecules. Just like the first step, this is also endothermic because we have to separate these molecules, breaking their intermolecular forces. So this is also going to be greater than 0. We'll call this delta H for the solvent. And then we have the mixing of the separated solute particles with the separated solvent particles. Now this is going to be exothermic because we broke all those forces and now we're going to have some forces as these particles interact, right? So this is delta H for the mixing of the separated particles. That's going to be negative. So if we talk about the overall formation of the solution, the change in energy for the solution will be the sum of those three changes. And so whether that's endothermic or exothermic depends on the magnitude of the individual terms. Some solutions release energy when they form and some absorb energy when they form. And this looks like one of those Born-Haber cycles, right? So, we're starting out with our solvent and our solute. They're aggregated, they're, in their normal state, stuck together by their intermolecular forces. We have to put energy in to separate the solute particles. We have to put more energy in to separate the solvent particles. And then when we let them come back together, we get this delta H of mixing is going to release energy. So if this release of energy is greater than the sum of the first two steps, then this will be an exothermic process. But for some things, the sum of the first two steps of separating the individual particles, that requires more energy than the mixing releases, and so that is an endothermic process. So why did we talk about all of that? Well, we're going to get to an equation here. So we can combine the solvent, separating of the solvent particles, and the mixing. We can put those two together and call them the heat of hydration. So delta H for hydration. So we just said that the heat of solution is equal to separating the solute particles, separating the solvent particles, and then the mixing together. So we're going to combine these two terms and call this heat of hydration. So, and here we're talking about aqueous ionic solutions. For aqueous ionic solutions, this is always going to be a negative number, and fairly large, exothermic, because we're replacing the hydrogen bonding between the water molecules with these ion dipole forces, which are stronger than the hydrogen bonding. Because here we have a full plus or minus or even +2 or -2 charge on the ions, and so that's going to be a large release of energy. So delta H solute, the energy involved in taking apart the solute particles, here we're talking about ionic compounds, that is the same as the lattice energy that we talked about before, just opposite in sign. Lattice energy is the energy change when these particles come together, and so delta H for the solute is the opposite in sign. It's doing the opposite reaction. So now we can just compare essentially the lattice energy and the heat of hydration, and the relative strengths of those are going to affect whether when you make the solution it feels warm or it feels cold. So, those instant ice packs, well, that has a substance in it that when it dissolves in water, it's an endothermic process, and it sucks energy in, making whatever is around it cold. Any questions?